In this video, we'd like to talk about the forces that we observe in electricity. Opposites attract, like repels, but not so much talking about the individual small particles like individual electrons or positrons, or the way we did in other videos, little circles with charges in them. Let's talk about bulk materials now. So imagine this is like a little aluminum foil ball, something you actually hold in your hand. It's not very small, but it is a conductor. And so again, because it's a conductor, we'll see that structure matter. I'll only draw this one time before we'll sort of dispel with drawing it in this detail all the time because it's not needed. So there's the protons in there that hold the structure together. And of course, with the protons in there, there's a bunch of little electrons around there as well. Here's all the little electrons coming in there. So it's a conductor. So what we know about the conductor is that the electrons are infinitely mobile. They move around very easily and very eager to do so. So what we're going to do now is imagine that we brought a rod near this thing. And by some means that we don't need to worry about, the rod was positively charged. So here's the rod all positively charged. So we ran the rod in some glass or fur. You can read in your textbook how that happens here. But we have a positively charged rod that we're bringing near a ball that's hanging from a thread, and the ball is a conductor. So the reason why it's hanging from a thread is because the ball can move now. It can swing back and forth like a pendulum depending on what forces might be on it. So the question is, what happens when I bring a positively charged rod near a hanging conductor? Well, what will happen is the following. So let me get rid of this too overly detailed view of matter that I was telling you about, because we don't need that detail to understand what these forces are. We'll get rid of it, but just keep in mind that the electrons are in there and ready to move. So what happens is that the positive charges on this rod are going to attract the negative charges in this ball. And so because the positive rod's over here, all the negatives, again, these infinitely mobile electrons in the conductor, are going to move over to that side because they're being attracted by the positive rod. But because all the electrons are over here now, what we're going to see over here is an area of the matter, the ball, that is sort of deficient of electrons. And as we said in a previous video, a deficiency of electrons actually means positively charged. So we're going to see a bunch of positive charges on this side. Now we're not talking about protons moving or anything like that. The protons don't move in the structure, and there's no positrons in there or anything like that. It's just that the electrons, which are infinitely mobile, have been moved away from their atoms that they might be in sort of a more equilibrium state. So the matter tends to look like this. A bunch of electrons are actually over here, and there are a bunch of nuclei over here without their accompanying electrons, because the electrons are over here, so they look bare or positively charged now. And now you can look at it now. You have these negative charges which are closer to the positive charges than these positive charges are. And so what will happen is the ball will actually just start moving this way. The ball will be attracted to the rod. Now we're going to be careful not to let it touch, but it's just going to look like this. It's just going to hang over. The ball would actually move and swing over like that. And yes, these electric forces are very apparent like that. The ball will actually move. The force is strong enough to actually move an aluminum ball, which might weigh several tens of grams even as it moves over like that. So it will move like that. And this sort of non-contact force that we see is often called induction like that, because we haven't actually done anything to the metal ball. We haven't touched it. We haven't transferred charge to it. All we did was bring a positive charge near it, and it caused these electrons to move to the surface and the positive charges to appear to move the other side through this induction process right here. But you will actually see the forces, which are very apparent. It will move like that. Okay, but we haven't had any contact. So as you might guess now, the next idea we're going to look at, let me just redraw this quickly here. So still have the same metal ball right here, again, full of electrons, ready and eager to move. But now what we'll do is we'll bring that positive rod near the ball, and we'll actually let it touch the ball like this. So here's that positive rod again, and we'll actually let it touch the ball like that. Now what happens when it touches the ball is that because the two materials are in contact, you can actually transfer charge from one piece of material to the other. So in a case like this, because this rod here is typically going to be an insulator, this is going to be something like glass or plastic, it doesn't have much charge mobility at all, and so any electrons that are in this material are going to stay put. But the conductor here, of course, has these infinitely mobile electrons, so not only will the electrons sort of move over to this side, and the positive charge will move over to this side as the rod is brought closer, but when the contact actually happens, some of these electrons that are on the conductor can actually jump off and become part of the insulator now. They won't move around very much, and the contact process is very inefficient, but some of the electrons can be transferred to the rod. And now what we'll do is we'll move the rod away like this. I'll try to just draw this again quickly like this. Move the rod away. So the rod maybe now there's some space between them like this. So there's some positive charges on here, and the electrons did get transferred onto this rod from the metal conductor. Now, it wasn't enough electrons to completely neutralize the rod, but these negative charges, these electrons, did used to be on the ball, and because they used to be on the ball the rod is now not the ball is not electrically neutral anymore. The ball is going to have a net positive charge because it lost some of its electrons. So the way you draw the ball now is something like this. Any form you want is fine, but it's going to look something like that. It has a net positive charge now. If you want, the induction can still occur. The positive charge can still move this way. The negative charge can still move that way. But the bottom line is the ball has a net positive charge because some of its electrons have been removed. And so now what you have is a predominantly positively charged rod with a positively charged ball. So the ball's going to swing over this way. This is evidence of like charges repelling each other now. So the ball's going to move over like that. So in the other case, remember in the induction, this is a contact sort of effect here. We actually contact, the two things were in contact, and we got that transfer of charge, and we see the effect we see. So when it was done by induction, the ball attracted. When it was done by contact, the ball initially was attracted to the rod and it was allowed to touch the ball, but as it touched the ball, it's going to jump away. That's the contact effect. And that's sort of the charge flow and the consequences of the force law. Like charges repel, opposite charges attract each other. The last and final way of seeing this charge effect on bulk objects like this is something that's very useful to visualize this, and it's called an electroscope. Now, Wikipedia has an excellent page on electroscopes, and you're encouraged to look at that as well. But what an electroscope is something that looks like this. There's like a conducting ball here and a metal conductor that goes down. And there's two leaves that are hanging down here, which are made out of very thin metal, often gold, so it wouldn't get corroded by the environment and stuff. But this point is that this whole device here is metal, and this square here is like a glass case around it that prevents air currents and things from messing up the effect you're trying to see. So we can do similar experiments, like say, for instance, we brought a rod here, this rod here near the electroscope. What's going to happen? Well, in the induction process again, because the electroscope is made out of all this metal, it has all these mobile electrons, a lot of the electrons, or many of the electrons that are in the metallic structure of the electroscope are going to be attracted upwards like that, to the top part, because they're attracted by this positive charge in the rod. But because the electrons now are hanging out at the positive ball of the electroscope, there's an electron deficiency down here, so these leaves here are going to sort of be carrying a positive charge, because you move the electrons out of their area. There's going to be positively charged now. What's going to happen to the leaves? You will see the leaves separate like this. They'll move apart like this. This blue leaf will move up here. This other blue leaf will move over here. You'll actually see the leaves of the electroscope separate like that because you've caused a deficiency of its otherwise neutral state down there. You pull the electrons to the top and they'll repel like that. What would happen in the contact case? Well, remember, we didn't let anything touch in that example right there, but if I draw the electroscope once again like this, here's the ball, here's the leaves, here's that frame again. Suppose I brought the rod in here and let them touch. So here's the rod touching the electroscope, say a positively charged rod like that. And as we did in the other contact case here, some of these electrons that are on that ball there can now be transferred over to the electroscope. So some of the electrons will go over here, there'll be some positive charge over here, and now we're going to pull the rod away. Pull the rod away, but because we pull the rod away now, and what we've done is the rod is sitting over here like this, has a few of those extra electrons from the electroscope, and so you've left the electroscope sort of in a net positive case because you've taken some of its electrons away. So here's the electroscope sitting here like this, and there's a bunch of positive charge now, but because the wand, you take the rod far away, get it way over like that, just get out of the way so that it can't have any of its induction effects anymore. This rod now is now left with a net positive all through it because you remove some of its electrons. It can't balance itself anymore electrically. And so what you have done here are these two mobile leaves with a net positive charge on it. So once again, as you might expect, these leaves are going to separate. This one's going to move up this way, and this one's going to move up that way. Kind of an interesting effect there that they both in the induction and the contact process, the leaves always end up repelling each other. And lastly, this second case here where the rod actually touched, I probably gave you the overcomplicated description, but I think that was a very intuitive one, is that once again you can have the electroscope like this, and here are the leaves like this, and here's the container that the leaves are in, is of course the idea of touching a positively charged rod all on this ball up here, so there's a bunch of positive charges on this like this. You can take those electrons away, but of course the alternative description is that you are actually transferring positive charges onto the rod like that. Of course, we know that doesn't happen from a previous video discussion. There's no positrons on the rod, and you can't get the protons to come off in these simple low energy cases that we're talking about here. But of course the alternative picture or an equivalent picture is that somehow you are rubbing these positive charges onto the electroscope like this. So you see, we end up, if you want to do the rubbing picture where the positive charges actually come off, we end up with the same picture as in the induction case. Either way, these leaves are going to repel each other. This leaf is going to end up way up here, this leaf is going to end up way up here. So that's sort of the electroscope, which is also evidence of these force laws here. And once again, you should always be able to explain how the electroscope works just using the force laws. That's opposites attract, once again, and likes repel. Using these force laws, you should always be able to describe any contact or induction scenario that you have in front of you. So your textbook has some examples of this, and you just should be able to look at them, and using the basic force law, you should be able to describe how electroscope leaves behave, or how a hanging ball would behave, both in the case of being contacted by a positively or negatively charged rod, or having some induction effect. But it's all about those forces.